Hello, my name is Alex Tiki, and this summer I worked with the DSI Summer Lab in Logan Ward to help make fast molecular simulations with minimal effort. So why do we need fast molecular simulations? The problem is that traditional molecular dynamics simulations are computationally expensive, but to further our understanding of these interatomic interactions, we need to run as many simulations as we can. From designing new materials for sustainable energy to understanding the fundamental behaviors of new compounds, rapid and accurate simulations can greatly accelerate our advancements in these fields. By making these simulations faster, we can explore more scenarios, optimize processes, and predict behaviors more efficiently, leading to quicker scientific discoveries and innovations. My research over the summer consisted of training a model that can emulate quantum chemical interactions. When I started on the project, there was already an initial pipeline for a model to run molecular dynamics. The model that was used was called SCHNET, which is a convolutional neural network specifically designed for predicting chemical properties of atoms and molecules based on quantum interactions. SCHNET was tested by having it try and emulate the process of dehydration, specifically the dehydration of propanol, but it didn't perform very well and had inaccurate results that didn't make good predictions. In these graphs, the blue line is the actual simulation that we're comparing against, the orange line is the performance of the initial model before fine-tuning, and the green line is the performance of the model after fine-tuning. The top graph shows the total energy of the system, the middle graph shows the distance between this carbon and this oxygen, and the bottom graph shows the distance between this hydrogen and this hydrogen. As you can see, the models aren't very close to the simulation it's trying to reproduce. Instead of trying to make SCHNET work, I decided to start from scratch and use a different model called MACE. Unlike SCHNET, MACE is a graph neural network, where each node in the graph represents an atom in the system, meaning it is much better suited for modeling molecular behaviors. Just like with SCHNET, I used the NE1X dataset for training, which contains 5 million molecules and their respective energy and forces. One of the pre-processing steps needed was to find the energies for each type of atom, which are also called the reference energies, by using a linear regression on the entire dataset. MACE subtracts these reference energies from the total energy of the molecule to get a target energy value that is used for training. The other pre-processing step was to convert the NE1X dataset from .h5 to .xyz, which is the format that MACE takes. After the pre-processing step was done, I made a script to run the training for MACE. I trained a lot of MACE models, each with slightly different parameters. I logged the results for all of my runs using the Weights and Biases website, and I found the best model and evaluated it against SCHNET. These graphs show the real energy versus the model's predicted energy, and these graphs show the real force versus the model's predicted force. There was already an improvement, with MACE's force predictions more accurate than SCHNET's. Once I had found the best model from the initial training and evaluated it, I moved on to fine-tuning. The first step was to rerun the molecular dynamics simulation for propanol. I ran it for 2,000 iterations, or about 1/2000th of a nanosecond, and saved it to an XYZ file for fine-tuning. After this, I continued the training for each model using the new propanol dataset and new reference energies. This time, the results were much better with MACE than with SCHNET. The forces especially had a significant increase in accuracy. After fine-tuning, I found the best model and used it to run molecular dynamics. It did much better than SCHNET, accurately predicting both the position and the energy of each atom. Although the model drops off in accuracy after about 1,000 iterations, this makes sense because I only trained it using a radius of 5 angstroms, and as you can see over here, it only starts to get worse after it crosses that threshold. Now, the whole point of using machine learning to run molecular dynamics was because it was faster. So just how much faster was it? Originally, running the propanol simulation for 2,000 iterations took me 70 minutes. Using the model, it took me only 2 minutes. The goal of my project wasn't to get a complete model that could perfectly simulate quantum chemical interactions. Instead, it was to prove that using machine learning to run molecular dynamics is not only possible, but plausible. With only a little bit of training, I could get MACE to pretty accurately simulate the process of dehydration. It requires very little new data to train new models, and then those new models can be used for running molecular dynamics much faster in similar environments. Thank you for listening, and feel free to ask me any questions during the Q&A or after.